Good morning, everybody, and welcome to this session about the IoTwins project. Let me share my presentation now to start our journey throughout the project. Okay, here we go. The IoTwins project is a project within the Horizon 2020 framework, and the long name is Distributed Digital Twins for Industrial SMEs, a big data platform. You will soon understand why this long name. Okay, let's start. Okay, this is me. My name is Francesco Millo. I am in Bonfigliolo since 2013. Bonfigliolo is an Italian manufacturing company which designs, manufactures, and distributes gearboxes, electric motors, and inverters. You will see later on why I'm telling you this. And I'm actually in charge of strategy and M&A, and recently in the recent years, also in charge of open innovation at Bonfigliolo. Okay, here is our project. The ultimate idea of this project is to provide a technological platform to small and medium enterprises able to lower barriers for jet uptake of Industry 4.0 technologies. What is the point? The point is that in this Industry 4.0 is developing pretty fast, but is something mainly developed and accessible for big companies. Sometimes billion companies, not less than that. So the idea here is to design a platform that is extremely flexible and that can be applied also to different companies, I mean from the one involved in the consortium, in order to lower the barriers, as I said, for small and medium enterprises. We're talking about a pretty huge project that costs $20 million, dollars and euros, and with 16 of the millions of funding from the European Commission, and 23 platforms, 23 partners. And I think that partners are actually the most important part of this project. Here is the summary of our consortium. So 23 partners coming from 8 countries. As you see, there is a bunch of companies coming from Italy. Actually, Bonfigliolo, you see, is a coordinator. That's why I'm here introducing you to this project in my role of a coordinator. But then from Italy, we have also Marpos, University of Bologna, and University of Bologna, you will see it later with Giuseppe Modica, he is the scientific coordinator. Then we have INFN, Arter, and Cineca from Italy, and several more from other European countries. I would like to pick some of them just to highlight a part of the content. You see, we could split our partners in 2 groups. Technological partners, when I say technological, I mean mainly research institutes, such as Fraunhofer, for example, Barcelona Supercomputing Center, and the already mentioned University of Bologna, Cineca, and let's call it industrial partners, so partners that actually involved mainly in the test bed. Then we have an exception is Blue Warrant, which is a partner helping a lot in the management of the overall consortium. Now, one of the key points of this project is to be able to provide top-of-the-edge services to each test bed. To do this, I would like to highlight that we have 2 important partners, Barcelona Supercomputing Center and Cineca, which are 2 of the 3 supercomputing centers in Europe. Cineca is the 5th in the world. BSC, I don't know, but still you can imagine it is one of the top 10s in the world. So this is something extremely relevant in the project that we are performing right now. The project lasts 3 years and starting in August, at the end of August 2019, and will be over in a few months this year. You saw maybe a pretty unusual logo here in this map, and is the one of a Barcelona Football Club. I will talk about it a little bit later. Okay, here is the project in a nutshell. The project is made of 3 parts. The first one is a technological platform that we are supposed to set up in order to provide services to 7 test beds or 7 pilots, and after that to 5 replicability pilots. Let me spend some minutes about the replicability pilots. Replicability pilots are those meant and so to demonstrate that our platform is not just suitable for the specific test bed that we are providing in our consortium, in our project, but also for other similar but not the same situations. Because again, the ultimate goal of this project is to have a platform able to adapt to similar scenario, but not just to the specific we are testing, and so to be able to act as a tool to lower barrier for SMEs. Now, the platform will be the one providing IoT services, the overall IT infrastructure for sure, big data services, AI services, and digital twins. Now, you see the name is IoTwins, the name of the project, and this comes for the merge of IoT services and digital twins. And this part, so the setup of the platform is, of course, led by those partners with the technological knowledge, and these are the ones you can see in here with their logos. These are just a part of them, actually. Then there is a lot of interaction with testbed leaders in order to understand how to set it up. You will see it later on in more detail with Giuseppe. And I would like to specify that we have 2 kinds of testbeds. The first type is manufacturing testbeds, and this is one of those in which Bonfiglioli actually is involved. And then we have facility management testbeds. About manufacturing testbeds, let me mention the one about Bonfiglioli and KK Wind. So Bonfiglioli is a leader in the production of gearboxes for wind turbine. And so together with KK Wind, as well involved in this sector, we are sensoring our gearboxes to provide predictive maintenance services to the OEM of beta, to the end user of the wind turbine. And then we have other tested with this kind of approach. About facility management testbeds, here I would like to mention the one coming from Barcelona Football Club, because Barcelona is not just a well-known sport club brand, but it's also a pretty visionary company, because they made this spin-off of a company named Barcelona Innovation Hub, which is in charge of serious innovation. And with them, we are developing a digital twin of the stadium, the Camp Nou, one of the biggest, or maybe the biggest in Europe, to optimize the crowd flow for safety and commercial reasons. And then we have the replicability pilots again. So meant to test the actual validity of what we found in the first 7 pilots, to see if they work also in similar but different situations. You see, for example, that the logo of Koala Closures is present both in the 7 pilots square box and those in the 5 pilots, because Koala Closure, that is a leader and the closure of spirits and beers, so is has tens of production plants throughout the world. And we are testing the first solution in their major plants, and then we test the same solution in the different plants that has different production conditions to see if it works properly, if the solution works properly. Okay, basically this is the idea of the platform and of the project. Now, today, we will go a little bit deeper, starting from the platform. And for this reason, I am leaving the stage to Giuseppe Monica from the University of Bologna, which is in charge to describe the technological platform. So let me stop sharing my screen. Okay. And now Giuseppe will show you a little bit about the platform.
Thank you, Francesco. Let me share my screen. Okay, good morning to everyone. Let me introduce myself. My name is Giuseppe Di Modica. I'm an assistant professor at the University of Bologna, and my research interests include cloud and edge computing, as well as big data, microservices, and some of the technologies that are the enablers of the platform that we have been developing in the context of the IoTwins project. So to start with, I will start by introducing some of the motivations that drove us in the IoTwins project, some of the guidelines and drivers and the goals of the IoTwins project. I would start with these assumptions. There are a couple of barriers that are hindering entrepreneurs, manufacturers from the achievement of what we know as Industry 4.0 technologies. So there are a couple of barriers that we can mention that needs to be torn down if we want that SMEs, so owners, can be, let's say, will be able to achieve the goals set by Industry 4.0. First of all, the low level of digitization. That's something that we need to overcome. We need those companies to start a strong digitization process. Second point is cultural barriers, some cultural motivation that prevents those guys from uptake the Industry 4.0 technologies. Of course, a limited spending power is something that is still in place, and the lack of in-house internet information technology skills. So those are a few not exhaustive lists of barriers that need to be torn down. And in order to achieve the main goals of Industry 4.0, one of this is, of course, the optimization of the production processes. And how do we optimize production process? We do it by increasing productivity, of course, and of course, taking care of the safety of humans that works close to machines. And also we want to lower the environment impact of our actions. So these are the drivers of the project, and the focus of IoTwins was set to the maintenance of machines that reside at the shop floor. Everybody knows that the type of maintenance that is run for those machines is kind of maintenance, programming maintenance. This follows the suggestions provided by, provided by machine vendors. Those maintenance, this kind of maintenance is run periodically according to this specification. But what we want to investigate is a new way of doing maintenance. We would like to suggests some kind of predictive maintenance. So some kind of models that are able to predict when maintenance has to be done. And that's good, of course, because it could save money, it could save costs, and it goes towards the direction of the goals of Industry 4.0, which is improve, optimize the production process. How do we do that? We would like to build digital twins out of physical assets. So specifically, if we have a machine, or if we have a machine part, we want to build a digital counterpart of this physical assets that is capable of reflecting the machine behavior, the machine status. And this will allow us to do some kind of monitoring, real-time monitoring on the status of the machines. But we want to do more than just monitoring machine. We want the machine to be able, the digital twin to be able to predict the time to fault, potential faults, or the probability of faults in the near future. That would allow us to trigger a maintenance right before that the faults occur. To do that, we need to build models, predictive maintenance models. We will leverage machine learning approach and simulation approach. So we want to leverage machine learning techniques to build digital twins. And for that purpose, we need to have big data. Big data that needs to be produced by sensors that are mounted on top of our machines. So we need to sensorize machines and let those sensors produce data that will feed our digital twin. And we're going to use, other than big data technologies, other technologies to implement, to develop digital twins. But basically, we need the basic assumptions that we need big data from the shop floor side. The specific IoTwins goals is not to build a generic model for doing predictive maintenance. We cannot do that. But we want to enable manufacturers, so manufacturing owners, the owners of enterprises, with easy to use tools and also affordable tools that will help them to implement their own digital twins. So this tool will have to hide the complexity of the underlying technology. And we are talking about IoT, big data, artificial intelligence, and microservices, edge and cloud computing. There is a handful of technologies that they need to cope with. But we want to provide them a tool that will hide the complexity of uptaking those technologies. And this tool will also enable them to implement digital twins by just using existing pieces of software, existing software entities, customizing them, compose them, so wire them together. And so in the end, they will just build by compose. They will adopt this kind of approach that will allow them to just pick some existing components, wire them together, and eventually they will have their digital twin. Another objective is to harness the potential of edge computing. Computing resources residing in the premises of the company, like even all off-the-shelf PC. It doesn't matter how powerful they are, but they can be used to implement some kind of edge computing. And since one of the objectives of this project is to build distributed digital twins, we're going to harness edge machines within the premise of the company in order to deploy specific parts of the digital twin in the edge machines located in the premise of the company. Last but not least, we would like to provide software developers, so third-party software developers, with tools to implement software components. As I mentioned before, digital twins can be developed out of a set of microservices. We're going to use microservices to implement those building blocks. But some of them we implemented in the context of the project, during the project. But we want to open the system to the research community. We would like others to be able to implement those building blocks and publish them and share them with the community. So in the end, the manufacturer will build its own digital twin out of a set of multiple building blocks that are available in a sort of catalog. So those are the expected outcomes of the project. We are going to develop, we are going to, let's say, finalize the development of an open and usable platform. So a platform in the form of a platform as a service that will enable manufacturers to, let's say, enact an agile development process of digital twins. So they will be able to develop, to integrate, to operate, to maintain digital twins in an agile way for the purpose of the manufacturing, of course. We will deliver a repository, a catalog of customizable and composable building blocks, as I said before. And we will also deliver a service development methodology and API that will be used to grow this repository. So we will allow people to use this API to create new building blocks that others will use to build their own digital twin. In this picture, I will show you how what we mean by how we interpreted the concept of digital twin in the framework of the project. So we're speaking here of a hybrid and distributed digital twins. So our digital twins is hybrid in the sense that we leverage two different approaches to develop the digital twins. One is AI, machine learning. So we have a kind of data-driven models. And we use also simulation. So we use simulation to, whenever we need some data that cannot be gathered from sensors for some reasons, so we build simulation to produce those data and to feed our machine learning models. Our digital twins is also distributed. So we don't want to build some software entity that runs in a central point, like in the cloud, but we want our digital twins to span different infrastructures, computing infrastructures that are available in the cloud continuum. So we may have a piece of digital twins running in a cloud instance. We may have another piece running in the edge nodes. And why not? We may have some piece of this digital twins running in the shop floor. Like, for instance, if we have an IoT gateway, which has, of course, limited computing power, but still it has computing power, we provide for pieces of this digital twin to run on top of that IoT gateway. So in this picture, you see on the left, in the blue box represents the premises of the company, of the manufacturing companies. On the far left, there's the industrial plant where machines are. On machines, we mount sensors. Sensors are in charge of, let's say, take data from machines and transmit those data Let's follow the red arrow below here, the data streams arrow. So those data are gathered first at the edge node, where there is a piece of digital twin running on top of the edge node. Here, data can be aggregated, can be anonymized, can be filtered, can be prepared for the next step. So we want to have quality data before calling up upon the machine learning techniques. Here is where data quality is obtained. So edge machines run on the streams of data, filter, polish, whatever is requested to do. And then those data are shipped to the cloud. On the cloud, we have, on top of a cloud instance, we have our machine learning model ready to be trained with those data. So huge data are flowing from the shop floor to the cloud through the edge. Here, those data are used to train the machine learning models. When the machine learning models are ready to execute, this model is moved back to the edge. You can see it here and on the top of the figure. The trained machine learning model will run on top of an edge and will be fed with data coming from sensors again. So in the first stage, sensor data will have fed machine learning model to be trained. In the second phase, when the machine learning model is ready to run, it will be fed again with real-time sensor data. Here is where they will run, of course, predictive maintenance. So those data will feed these machine learning models, and they will predict potential faults of machine. Something more, let me deep dive into the platform. I would like to skip this, as Francesco already mentioned it, what the methodology to develop the platform is. So just to remind that we have two phases. In the first phase, we collected requirements, and then we developed the platform. The platform was tested by 7 partners in their own testbeds, so they integrated their testbeds with the platform. But then again, other so-called replicability testbeds integrated with the platform with the purpose of, again, increase the functionality of the platform, but also, of course, validating the developed product. This is the basic logic architecture of the platform. It's a layered architecture. On the bottom, we have resources that are virtualized by the resource middleware layer. We virtualize any kind of resources. Doesn't matter if they are in the cloud, in the edge, or even in the in the enterprise premises. On top of that, the resource management layer is responsible for managing these resources. And on top of this, we added the platform service layer. This is where we provide data and services to develop digital twins. And finally, at the application layer, we have, sorry, I should have go on with this animation. We have all these services that we need to run our predictive maintenance algorithm. So data analysis, machine learning model, trained model, and of course the simulation, as I said. These are 2 cross layers that we need to provision identity management and access. And of course, data encryption in case that any of the testbeds would require data encryption of data when, for instance, those data need to be shipped to the cloud and then they need to go back. An overview of our architecture, as I said, we virtualize resources in the cloud continuum. So the architecture you saw in the previous slide is replicated each of the three computing infrastructure. So at the cloud end, on the edge, and let's say on the machine, on the shop floor. So we provide again an underlying layer of virtualization of resources. On top of it, we add data for building digital twins. In that case, you see that we have several applications according to several components according to the infrastructure that we are targeting. Specifically for the edge, you may see, for instance, what kind of data we are speaking about. So entity for collecting data, for streaming data, for processing data, entity for the persistence, and so on. And this is the core of the platform. The platform is based on the Indigo product, which is a product provided by one of the partners of the consortium. And the platform has been, that product has been enhanced in order to account for other requirements coming from the testbeds. But the platform is based on an open source platform that with the Apache 2 license. It supports several virtualization environments. It has an orchestration engine that is based on the Tosca language, so a very well-known standard for orchestration. It has an identity and access management. And currently, the prototype we developed has got a TRL 5, so it's not ready for the market, but we are just developing business models, and we are also studying how to launch this product on the market. Those are the extensions that we have developed in the course of the project. Like, we are able now to include the edge among the resources, the computing resources that are available for building digital twins. We have added a service catalog. We have added support for data management in terms of data storage and data stream. So in the end, what makes it up a distributed digital twins? If a distributed digital twins is composed of a data pipeline, so you need to build a data pipeline that sustain the digital twins, because we need to transfer data to feed the digital twin, and data processing elements. We may have data filtering, data aggregators in the edge, but we may have, of course, machine learning processing elements that will do the maintenance, predictive maintenance work. We adopted a topology-based approach. So the end user, if they want to define a digital twin, they just have to define what the topology of the digital twin is in terms of what are the building blocks and how these building blocks relate to each other. So it's a matter of defining some kind of graph of building blocks and putting everything together. So the end user declares the digital twin topology, and the platform will take care of deploying the digital twin. If I have time, I'll just show you a very simple example of how to deploy, of how the platform will deploy a distributed digital twin in the cloud continuum. So we start with the sources of data on the left end of this slide. In this case, they are MQTT-enabled sources of data. It doesn't matter the type of data that they are going to sense. Here is in this purple box, we have depicted the edge node. Let's not forget that sensors and edge node are in the premises of the factory. On the right side, we have a cloud instance. We're going to use a cloud instance for a specific purpose. So when data are gathered from the machine floor, they will reach an MQTT broker. Here, for instance, those data will be stored in a time series database like InfluxDB via this connector that we have implemented. So the connector will subscribe to the MQTT broker to get the data stream and to store those streams to the InfluxDB. Here, data polisher will run, will take data from an InfluxDB, and will produce the quality that is requested for the final purpose of implementing the maintenance, the predictive maintenance. Once those data has been polished, data are shipped to the cloud, where we have cloud object storage like Min.io. That's another building block of our catalog. And here we have a machine learning model that will be trained with data, with quality data stored in Min.io. Once the machine learning model has been trained, the cloud here, where it is ready to run, it subscribed, of course, to the MQTT broker, because he wants to consume data, real-time data coming from the MQTT-enabled sources. And whenever a fault is detected or is about to be detected, or potential fault is about to be detected, it notifies some entity which is responsible for instance, running to or triggering the maintenance of the specific machine. So this is the basic cycle of our predictive maintenance process, and this is how easy it is to build a digital twin. So digital twin is made up of these components that need to be wired together, and we believe that with this approach we have democratized the access to technology also for people who are not skilled, and we hope that this will help manufacturers, owners, with the help, of course, of some IT skilled people, to implement digital twin, not just for the purpose of predictive maintenance, but for other purposes. That's it. A few words just to mention that, of course, these building blocks are implemented as Docker containers, and we publish this in a service catalog, which is available, which is open to anyone for use. That's it. Thank you. I'm done. I don't know who's next, but
it's me, Giuseppe.
Oh, Andrea, yeah, it's you. So I will leave the stage to my colleague, Andrea Borghesi, who will provide more details on the services, on AI services that I've just mentioned. Andrea, the stage is yours.
Thank you, Giuseppe. And thank you, everyone. Unfortunately, you cannot see me because, of course, when you really need it, Zoom abandoned you. So there is no reason why my webcam is not working. I'm deeply sorry for this, but we will do it anyway. I mean, I'm going to share my screen now. So, okay, I will be quite brief because Giuseppe has been really exhaustive in his introduction about the tools and the services provided by the IoTwins platform. I wanted to give you a few more details about the actual service catalog, the higher level, say, services that have been offered on top of the data platform to solve the actual task addressed by the IoTwins, by the digital twins. So, as we probably already understood, with IoTwins project, we aim at offering multiple tools stemming from the artificial intelligence field, and these tools will be used to create the actual digital twin. We had a few main, let's say, principal ideas of how we have to prepare these services, and especially the focus is on the reusability of these components, the possibility to compose the single sub-services into larger workflow, and very importantly, we developed and deployed these services to be as easy as use as possible, because the underlying idea of the IoTwins project was to bridge the gap between artificial intelligence expert and practitioner and small and medium enterprise and any kind of user who has no background in artificial intelligence. In general, the artificial intelligence services covered by the project are very heterogeneous, and they deal with a wide spectrum of needs. But in general, we can identify three main categories. machine learning and deep learning, and this is especially true when we have big data and we want to extract information from this big data. Also, simulation models, very important. I get back to them for a second. And finally, optimization model as well, which we try to make as, let's say, transversal as possible. So again, the main idea that we had is we wanted to bridge the gap between AI expert and SMEs and facility manager. And the two main issues is this, is that in general, AI experts do not provide sufficient support for these, say, lower tech level user. And the second thing is that people working in SMEs and facility and larger complex facility might not even know the availability of AI tools to solve their task. And a big aim that we have in this project is actually to demonstrate how artificial intelligence techniques can actually be used to address real world problems. And then the idea that we have is we developed a series of services, and we started by developing, let's say, general services, AI-based, that can be applied to multiple different use cases. And then we also wanted to provide a series of clear guidelines, workflow description, a very detailed documentation to highlight how these services can be used. And this is the first step. And also we wanted to demonstrate how these services can be instead also tailored to meet specific needs by the new users. Just to give you an idea about the data that we are dealing with in this project. The project is very heterogeneous, and we have, as you've seen, multiple test beds from very different domains. But in general, we have a lot of data which might be labeled or unlabeled, and the data is generally under the form of multivariate time series. This is very important because with this kind of abundant data, it's very natural to think about using predictive models that extract pattern from this big amount of data and offer insights to user about the data that has been collected. And this is the typical, let's say, arena where deep learning models really shine. I also wanted to point out that while the data available is large, I mean, from the system that we are monitoring, we are collecting really a huge amount of data. Having a lot of data by itself, it's not necessarily a magic. It's not necessarily everything that is needed, because, for example, to train a machine learning model, you need to have high quality data. You need to have data which is in general well formed and it is labeled. For example, telling if the system at any different point in time is in a normal state or in an anomalous state. And this is not always the case. Why is that? Because while collecting data is easy, annotating the data is not easy. It's really not a trivial operation. It's really time consuming. It requires human understanding. So this is one of the reasons why simulation models are also very important, because simulation models can help generate synthetic data when the big data which is available is not sufficient to characterize the system behavior in all possible scenarios. In that case, the simulation model can instead really help. As Giuseppe has told, the services have been developed as a containerized application, so I'm not going to bother you here with another more details here. You can find a YouTube video where we demonstrate how to use some of the most general and, let's say, user-friendly services. This is instead, let's say, not exhaustive list, but I wanted not to show hundreds of different services here, so I selected, let's say, a few samples of the services that we are offering. You might notice here that a good amount of services, so from generic processing until the time series forecasting with the recurring network, these first services are all belonging to the machine learning area. So these are services that might be used for predictive maintenance tasks. We also have here, you see, some simulation-based services, because as I told you, simulation is very important to generate synthetic data when not all scenarios might be explored, because, for example, one cannot put a critical system in a critical state just to measure the response of the system, because that will break the system, of course. So simulation is fundamental. Also, we have optimization services which are somehow transversal to all test beds. So, for example, hyperparameter fine-tuning is very important, because when you want to create, for example, a service to do remaining useful life estimation using a deep neural network, which is a type of model belonging to the machine learning area, there are a lot of parameters to this model, and how to fine-tune, to calibrate this parameter is itself a very complicated issue. So we devise as well an optimization service explicitly to address this issue. This is the view of the services from inside the private repository that we plan to make public by the end of the project. This is a very, very quick example, just not to bother you about the documentation, just to clarify that these services have been documented very, very clearly. We are working on this as well, but by the end of the project, we will publish a very detailed documentation of those services. And just to remind you, we have these two main views. So we have the platform that offers already a series of services, and the user can log into the platform and can select one of the already general purpose services that are available, and with a web interface might interact with the platform, feed data, and launch the actual services, and the orchestration tool will be in charge of actually deploying the actual service. Then we also have an interface for service developers, because, as I told you, it's important to notice that while we offered a quite comprehensive series of already working services, a more experienced user might want to tailor the service for his specific needs, to customize the actual, for example, machine learning template to fit their need. And for this, there are a lot of instruction and documentation on the IoTwins platform and IoTwins document repository to guide people, and especially new service developer, on this important activity. I wanted to conclude this presentation with a very rapid, very quick demonstration of two services that have been developed in the IoTwins platform in the last couple of years. The first one is with predictive maintenance, and in particular, we have a testbed which is, devoted to the creation of caps, bottle caps. So the idea here is that we have a molding extraction machine for which we need to know in advance if any components in the machine is going to break. This is the typical task, which is called remaining useful life estimation, and it is a very, very important task in the predictive maintenance world. And we decided to tackle this challenge using the vast amount of data collected in a couple of years since the start of the project. That data collected from one of the critical machines at the industrial plant that is producing these bottle caps. And then we applied machine learning techniques to extract information from this data and obtain a predictor that tells us, okay, the machine is working fine, okay, in the next hour we think that something is going to break, and so whatsoever. This is the general architecture of the overall system. So we have edge machine that are monitored. So this is the data coming from the edge, from which we collect the data. And then we have also high performance computing system capability that are used to actually train the machine learning models. This is the actual machine. This is a molding machine for which we want to measure the abnormal wear of the bearing coating. And basically, we have a series of integrated sensors that tells us, that creates a multivariate time series from which we can extract the actual information. And I wanted to show you finally, we apply a temporal convolutional network, which is a very specific and novel type of deep learning method. Temporal convolutional network has been introduced let me think, in 2016, but they gained popularity around 2018, 2019, and are very, very good to deal with time series data. And in this case, we see we have an anomaly. This was artificially injected because this is say, not a production machine. This is a test machine that we have been using for a special purpose. And you see here, when the anomaly is introduced in the normal operating condition of the system, you see that this is the prediction of the remaining useful life estimation of our prediction model. And you clearly see that when the anomaly arises, when the failure arises, you see that the rule, the remaining useful life estimation, steeply decreases according to the fact that actually we can in advance see that a problem is going to happen. Another testbed I wanted to show you finally. This is a replication testbed. So this is a testbed when we applied the methodologies devised for different testbeds. We applied it to this one, and the goal was to see if there was a way to transfer effectively the methodologies devised for previously addressed issues. And this is a case as well of manufacturing predictive maintenance. And in particular, here we are monitoring an automotive engine industry. And the goal is, again, from this data that is collected from an automotive energy industry, and then again is composed by a multivariable time series, we wanted to automatically analyze and identify critical situations. So in this case, the idea was not predict in advance the situation of the system, but we wanted to, by looking back at the process that has just completed, to automatically distinguish faulty from normal ones, so healthy production processes from unhealthy ones. And in this case as well, we applied deep learning methods to the data that have been collected in the last couple of years. And in particular, there is another, let's say, trick here, because the data available was not, the vast majority of the data in this case was clearly belonging to normal situation, because the data was coming from real production, in production manufacturing system, so system that have in general 99.9% of say availability and success rate. So the data representing abnormal situation was very scarce, and in general machine learning models struggles when they have to face very, very unbalanced datasets. So in this case we created a series of services which start by preprocessing the data and which start by augmenting the data, so injecting synthetic data that emulate the behavior of a system in a faulty state. And then we applied again deep neural network, in this particular case convolutional neural network, to actually distinguish anomalous situation, anomalous process from the healthy one. And this as well has been very, very effective, with high accuracy rate in the order of 95%, if I remember correctly. We are finalizing and validating the number, but those are the validation number are very, very promising. And so this is another success story that we were very, very happy to see fully realized, and that's why I wanted to talk about this. And I think I've exhausted my time, and I also completed my presentation. So I thank you everyone for your attention, and I'll stop sharing now. Thank you everyone. I don't remember who's next now, probably Bonfiglioli, or is there any kind of break?
Yes, start the video. Good morning all. My name is Roberto Lambruschi, and I'm team leader for the wind energy business in Bonfiglioli. With my colleague Paolo Cominetti, Adriano Costanzo, and Luigi Presti. We are working on the IoT project, and so on the introduction of the sensor in the gearbox. Bonfiglioli, it's an international company that produces gearbox, motor, and frequency converter, split in 3 different business units: industrial, robotic, and construction and wind, with plants in Europe, Asia, and America. Some years ago, we started to study the IoT on different application and market in order to collect data from the field, delivery, and make post-processing. The scope is to understand the real working condition of our device, calculate the real damage in order to schedule in advance maintenance activity and avoid failure. With the IoT project, we made an additional step that we will see later. Go deeply in the wind market. Bonfiglioli is a leader of yaw and pitch system. The yaw drives are dedicated to the nacelle rotation to follow the wind direction, whereas the pitch drive are responsible of the blade position in order to maximize the energy production. The Bonfiglioli product range cover from small turbine to the giant that we can see in the offshore application up to 15 megawatt. Here we have an example of our product range that include the frequency converter, electric motor, and gearbox for the yaw system and the pitch system. The wind energy market, in order to be competitive with the fossil energy, need to reduce the cost of energy, LCOE. Less cost of the turbine and less cost of maintenance means less cost of energy. And in order to obtain this goal, the target is on one side to increase the dimension of the turbine in order to split the fixed cost. And so the turbine is becoming more and more bigger. On the other side, another way to reduce the cost of the energy is to reduce the cost of maintenance. And an option is to introduce the IoT that has for sure an initial cost, but with the positive result of reduced maintenance and avoid stop of energy production. The solution is based on torque sensor and that translate the magnetic signal into a torque, and an additional vibration sensor in order to detect some abnormal working condition inside the gearbox, with the scope to introduce a maintenance in advance. As already explained, the European Commission inside Horizon 2020 has activated a project to stimulate the introduction of the IoT in the industry, and Bonfiglioli is one of the partners for the wind energy business. For this reason, we chose on the field an old turbine already installed some years ago, and we estimated the cost of maintenance of this product. And in 20 years, we noted that the maintenance due to the failure inside the turbine, it's around 120 kilo euro. Plus, there are at least 80 kilo euro of missing of energy production. And this one was due at least for 6% due to our gearbox, or in general to the gearbox. Based on this information, the fact that turbine work 24 hours per day, the necessary to reduce the cost of energy, the cost of the yaw drive, the downtime, the loss of production of energy, and the repair cost, we introduce the solution of the sensor in order to collect data with the SCADA and calculate the residual life of the gearbox with the final scope to introduce the predictive maintenance in our drives. So with an end user, the park owner, wind energy park owner in the field, we identify in north of Ireland a park with some old turbine. We introduce our gearbox with sensor directly in the field. In the same time, we create a backup solution in our bench test with the same drive and with the simulation of the load of the field. And we collect the data also from this based in order to compare the result, the data with the field one. Now I give the control to my colleague to go deeper in the sensor explanation.
Thank you, Roberto. Okay, to meet the needs of predictive maintenance in the wind sector, we have chosen the following architecture. For this solution, we monitor and analyze only the yaw system of the turbine. It allows the rotation of the nacelle. In this architecture, the most important aspect is the data acquisition. The data sources are mainly two. The first is provided by the SCADA system that controls the entire turbine. It provides us information about the status of the turbine, and for us, they are our boundary condition and are essential to better understand the signal arriving from the second source. The second data source is given by our smart sensor developed by Bonfiglioli and by the torque meter that give us the output torque and speed value of the electric motor. Through it, we reconstruct the real data cycle of the yaw driver. All data and signal are acquired by our edge gateway, which process and compress the data, and then send the raw data and process data to the cloud. Next slide, Roberto. Thanks. Okay. There are three predictive maintenance enablers for us. The sensors is in this case made by Bonfiglioli, which allow us both to acquire signal through internal sensor, but also to acquire external sensor such as torque meter. The edge gateway that acquires, process, and send data to the cloud, and finally the cloud, which allow us to save raw data that can then be analyzed with other cloud tools, for example, artificial intelligence and so on, and view the low frequency data on the dashboard. Next. Okay. For this solution, we used commercially available tools or solution already known in the industrial world in general. While on the sensor side, we decided to use a proprietary Bonfiglioli solution. Our smart solution has both internal sensors such as the accelerometer, magnetometer, and temperature sensor, but also have the possibility to acquire analog signal in voltage and in current. It also has RS485 port for reading a third-party digital sensor. It communicates via Wi-Fi, and it can be powered either at 12 and 20 volts in DC or via power over Ethernet. Okay.
So now we will go deeper into the technical solution at the edge gateway level. On the left side, we can see the technology stack from hardware point of view. Instead, on the right, there is the software technology stack that we have used. So for the hardware stack, we have created a sort of box that contains all the elements, all the ingredients that allow us to collect data from several kinds of applications where the Bonfiglioli products are involved. So not only wind, but also mobile, discrete manufacturing, motion, and robotics. So there included the edge gateway, obviously, the Wi-Fi access point, or the 3G, 4G modem, some Ethernet ports, some digital input, and also digital and analog input that allow us to collect data both from our sensor, but also from external kind of source or from other inverters, PLC. And also the possibility to and the power input, obviously. And on the left side, instead, it is highlighted the software technology stack. It is a classical software architecture in microservices, and each and also event-driven. Each module is contained in a Docker container, and the software stack run on Linux. We use several programming languages, but I would like also to highlight that each module has its own responsibility. So we have the device connector that collect data from sensors, external sensors from the field. The preprocessing modules that allow us to clean the data, to synchronize the data or fill the gap that we could have into the data. Then we have some processing module where we run our predictive maintenance models. The cloud connector that connect our edge to the cloud services of IoT provided by IoTwins. So collecting both high frequency data and low frequency data, and also some infrastructure and core service modules that allow us to have some orchestrator or data logger, or for instance a local dashboard that allows us to monitor better the situation or to commission the local application. In the next slide, instead, we have the graphical interface that I have mentioned before. On the left, the ones that we can use in the cloud to analyze the low sampling frequency data. Below, instead, the other one is the Minio browser, obviously where we can download the files that contain high frequency data, but also some contextual data related to when this data was acquired with torque, speed, wind, direction, pitch, angle, and so on, in order to be analyzed by the more advanced tools, like, for instance, MATLAB. Instead, on the right, we have an example, an extract of our dashboard, the monitoring section, where with some drag and drop, you are allowed to add some widgets that allow you to monitor the local situation, obviously for commissioning. Now we have a video, a video that demonstrates the result of this data collection in the digital twin. So there are two windows. The one on the left-hand side is the IO system model, and the other one on the right-hand side is 3D visualization of the system. The model consists of 5 parts: the control system, the motor, the fault, the nacelle, and the aerodynamic model. The input signal of the motor, you see, are the pitch angle, the wind speed, wind direction, and the IO model has 4 electrical motors supplied by AC voltages, and there are some switches that change the direction of the rotation of the motor. 2 types of faults has been added to the model that are the broken connection and additional losses, and the amount of fault can be changed, obviously, programmatically. The aerodynamic model includes 3 blades connected by joint to the shaft of the wind turbine. A simulation test here you can see has been implemented on the model. So you can see from the figure that there are several situations from 0 to 10 seconds, the model worked in the nominal case. And at the moment of 10 seconds, a fault, additional losses, was triggered. And it can be seen that from a torque signal of the motor, the torque increased and became larger. So we have a peak in the that is larger than the nominal torque. And at 200 seconds, there was another fault, the broken connection that was activated. And again, you can see the torque that had a different behavior compared with the nominal torque. So from us, it's all. Thanks a lot. So now I think is I can leave the stage to another colleague. Thanks.
Okay, thank you from Bonfiglioli. I think it's my turn again, and the report case again. So now I will be discussing a different aspect compared to the ones that I have shown you before. So rather than going, let's say, on a general overview of the services, I will give you a bit more detail on a specific use case that we have tackled during these 3 years. So let me share my screen. Let me share my screen, and I will talk to you about Eczema, and in particular the monitoring and the series of predictive maintenance application that have been applied to a large scale supercomputer. In particular, here in Bologna, I am from Bologna University. Here in Bologna, we have the largest Italian supercomputing center, which is called Cineca, really just outside of Bologna. And at Cineca, we have plenty of large computing facilities. High performance computing center, which is another name of supercomputer, is in general a collection of hundreds and hundreds up to thousands of computing nodes. In general, high performance computing systems are really complicated machines that needs to be carefully managed. Their behavior is very strongly and strictly regulated because their power consumption, for example, is very high. So the workload management need to be extremely well regulated. On the other hand, since we have hundreds of thousands of different components, because you have to imagine that each computing node is composed by hundreds of smaller components, such as CPUs, hardware accelerator, memory banks, and so on. Since we have so many components, it's very hard to keep track of all of them at the same time, and it's very hard even just to know when one of these components breaks down. Let's say the dream would be to predict in advance when a component, for example, the fan in node 1200 is going to break down. But already the detection in real time of a problem in a supercomputing center is very complicated. The good thing is that since this is a supercomputing center, so since we have many sources of data, the amount of data is really huge. This is a really a situation when the term big data can definitely be applied. And in particular, in the past, we have developed a monitoring system which is called Eczema, which stands for exascale monitoring. Exascale represents the 10 to the 18 number of floating point operation per second, which is let's say the evolution towards which the supercomputing are increasing the power computing capability. And we have developed since 2015, 2016, so even earlier than the beginning of the IoTwins platform, we developed a monitoring infrastructure. And thanks to this monitoring infrastructure, we are able to extract a lot of very fine-grained and precise information from the supercomputer itself. This is crucial because this allows us to collect a lot of data, and then this data, very fine-grained and very detailed, allowed us to create a series of machine learning-based models to, let's say, identify the right or wrong behavior of the computing nodes. Just to give you an idea, this is Eczema at 2021. We are currently expanding it to cover even more computing machine. But supercomputing machines, but just to give you an idea, Eczema has been deployed at Cineca data center since 2015, and we are collecting a lot of data. Basically, we are collecting a couple of terabytes of data every 3 weeks. We don't store all this data in raw format because that would be a nightmare in terms of storage space, but we compress the data, we discard the data which is less useful, so we keep a smaller amount of the overall data. And those are 2 machines where Eczema has been deployed, and in particular Marconi M100 is the current top level machine supercomputer at Cineca, and it has more or less 1,000 nodes, each one endowed with 4 very powerful graphical processing units. And we have a series of monitoring component, a series of sensors which are attached, installed on to each node. Thanks, partly we are using custom-made sensor, and partly we are exposing the already existing sensor and power performance metrics that are available in nowadays computing apparatus and computing units. And just to give you an idea, this is the variety of different data sources that we collect from Marconi and Marconi 100. I don't want to go into many detail here, but I just wanted to give you an idea of the different number of metrics that we are collecting. So we are collecting almost 1 million of different metrics. Why is this? Because we have thousands of nodes and we have thousands of components which are measured in any node. For example, we are measuring GPU load, we are measuring GPU power consumption, we are measuring GPU temperature, we are measuring the utilization percentage of each core in the computing node, we are measuring the clock frequency of each core, we are measuring the fan, the speed of the fan, we are measuring the power consumption of the cooling units, we are measuring the room temperature where the servers are stored. So just to give you an idea, this is the order of magnitude in terms of number of features that we are using to characterize the behavior of the supercomputer. So no need to remember all these different nodes, all these different names, but the important thing is just to give you an idea about the scale of the problem. This is a really large scale monitoring infrastructure. And this is the, let's say, overview of Eczema. So Eczema is basically a collection of data broker which are held together with MQTT and a series of off-the-shelf components such as Nagios, Kairos DB, Spark DB, and whatsoever. But this is low-level technical details which I will skip, to be honest, and not to bore everyone. But I wanted to give you an idea instead how we use this data, how we use this huge amount of data to gain some actual useful insights. Okay, the first thing that we've done was to devise an anomaly detection model, an anomaly detection approach. As I told you, this is very important because while supercomputing systems are monitored continuously by the system administrator, it's not easy for the system administrator to know in real time when something is going on or not, when something is happening as expected, or if there is any kind of malfunction. This is very, very complicated for system administrator. So already having an automated tool, a software tool that tells us, that tells the system administrator the node 15 is in a good shape, or the node 16 is in a bad shape, is experiencing a fault condition. This is very important. And this is the first thing that we have done using the data that we have been collected from supercomputer at Cineca. And this is in particular, we then applied a specific type of deep learning method, which is a type of deep neural network, which is called an autoencoder. And the autoencoder is trained on the historical data collected since 2015, and then it is used on live data to perform online inference. So on live data, after the training, we can use this model to automatically detect if there is an issue or not in any of the node composing the supercomputing system. It's important also to stress out that in this case, the machine learning component, the autoencoder, is not requiring any kind of annotation. Its basically only requirements is that it has to be trained on a couple of weeks of normal data. So we need to be sure that we have the system, the overall system, in a normal functioning condition in the first couple of weeks, for example, of its existence, and then we can train this machine learning model, which can then be used on live data without any kind of label, which is a very important thing. And just to give you an idea about the results, because this is actually what is important, here you see the actual, let's say, anomaly signal provided by the autoencoder. This is for a specific node in Marconi 100. You see here you have the temporal line in the x-axis, and in the y-axis you have the reconstruction error, which is a measure of the provided as output by the deep neural network. When you have this period of time highlighted in red and blue here, this corresponds to anomalies, to fault condition that we injected in the system to test the validity of our approach. And you see that in general, the anomaly signal is higher, definitely higher, compared to the normal situation when we are in a faulty condition. So the idea is that we can then use this anomaly score, and after having identified this yellow line here, which is our threshold, which can be identified using some subset of data, keep it apart for this validation purpose, we can automatically detect faulty conditions simply by looking at the reconstruction error. If the anomaly signal is higher than a threshold, then we can claim that the situation is not under control. The situation is faulty. And in practice, within production anomalies, we have reached around between 90 and 90% accuracy. But we also can do better. We can do better because since 2019, we also had access to label data. So not only we have access to a couple of weeks of data that we know that correspond to normal working condition, but we also have information about the status of the system of each computing node at any time point. And the idea is that if you can use this label, you can actually do even better, because if you use this label, you can build more complex models. You can build models which are even more precise, again, deep learning model in this particular case. And these models can be also used not only to detect anomaly, but they can also be used to predict the anomaly. And this is very, very interesting for us. This is a supervised approach because we are using the information stored in the label. So we have information at each point in time if the node was in a normal condition or in a faulty condition. And I wanted to show you here, the blue line here, you see, which is called label in the graph. The blue line corresponds to the period of time when the system administrator realizes that there is some problem in a specific node. So when the blue line is at 0, the node is in a normal condition. When the line goes up to 1, this means that the system administrator recognized that there was a problem with this specific node and he set a flag to 1 to say to his colleagues, okay, this node is down, this node needs to be fixed. Why this is interesting? By itself, it's not interesting, but I wanted to show you then the anomaly signal, which is this yellow-orangish line here. The anomaly signal is, again, from 0 to 1. When 0, the anomaly signal means that our deep learning method tells us no problem, whereas when the anomaly signal goes to 1, this means that the deep learning model is telling us there is an issue. The good thing here is that you see the blue line is exactly corresponding to the yellow line when the system administrator noticed the problem. So we are doing as well as the system administrator when detecting the anomaly. But the very interesting thing is that our model, our deep learning model, start recognizing that there is something strange going on, some weird behavior which is not exactly corresponding to normal situation, even earlier than the insurgency of the label. So even earlier than the period in time when the system administrator actually realized that there was something bad going on. So basically, this deep learning model with this anomaly signal can tell us in advance, can anticipate the insurgency of an anomaly, of a fault behavior. And on average, on Marconi 100, on considering all these 1,000 more or less nodes, we beat, let's say, the system administrator by an average of 1 hour and a few minutes, which is a significant improvement. I mean, it's a very welcome improvement for system administrator. I also wanted to give you an overview of two different tasks that we have tackled with artificial intelligence after having collected all the data from different supercomputers. And in particular, another very important issue in supercomputing center is the power consumption. The power consumption of a high-performance computing system is really, really a big issue. It's a big issue because these machines tend to consume in the order of hundreds of kilowatts. So they are really, really power hungry. And this is especially true when you reach, for example, in Italy, summer season. So it's very hot. You need to cool down your machine. So in the summer, the power consumption increases because you have to spend more energy in keeping up at, let's say, a higher level of execution, the cooling system. And for this reason, it's very important to have a knowledge before an application is submitted to the high-performance computing system to know its power consumption. Why this is important? This is important because if you know in advance that your application is going to consume a certain amount of power, is going to require a certain amount of power consumption, you can then decide an optimized schedule. So you can decide, okay, maybe this application, I will start it at 4 in the morning, and instead this one, I will postpone it at 6 in the morning, because I know that from the energy profile that I have collected yesterday, and from the weather forecast, I know that the day is going to be very, very hot, so I can rearrange the starting time of my application. Okay, this is very nice. This is what we call the prescriptive maintenance, because this is live maintenance that allow us to optimize the future behavior of the system, of the target system. But there is an issue here, because of course it's not easy to know in advance the power consumption of high performance computing application, because user typically have no idea about the power consumption of their application. But the good thing is, if we have a lot of data, such as in this case, we can extract this information using techniques, again, from the deep learning area and machine learning area. And in particular, using a machine learning model, which is called a random forest, which is basically a collection of decision trees, for those who have any idea about machine learning techniques. And using a random forest, we obtain a very, very good estimate in terms of what will be the power consumption of all my application, for each application of my HPC system. And thanks to this prediction, we can then devise a smart scheduler that handle the workload in a, let's say, in a more proactive way. So handle the workload not to, for example, cause overheating or cause problem with the power supply line. Finally, another very important thing for a system administrator and facility owner is to understand why the job, so the application that user submit to this supercomputing center, why the job fails. Because job fails for a variety of reasons. One might fail due to systemic error in the, for example, when the network goes down, when the internal network of the supercomputer goes down, this in generally causes a spike in failure rates for all type of jobs. Instead, we might have situation where a job fail due to a software bug, because maybe a user developed this software, developed this application, it submitted to the supercomputer, but then fails because there was some underlying bug that was not noticed until reaching the production phase. So it's very important to system administrator to know if there is let's say a suspiciously high amount of failure in a specific point of time. And we also developed a series of indicators basically on a measure of entropy in terms of how many jobs are failing at the same time and belonging to the same user. And thanks to this method, it's possible for the system administrator to detect on live data when there is a higher probability of a systemic root, a systemic problem in the system, or rather if you are experiencing, or is the system rather experiencing a high level of failure due to a few users that submitted multiple applications with some bug inside. And this is it, I guess, because there is, I mean, I have no more time, but just finally, just to give you another idea, we also developed a prediction model to automatically predict, to estimate the remaining useful life of hard disk. Hard disks are very, very important and a critical component of computing center. Is not easy to know in advance when they will break down. And again, in this case, deep learning model can come to assist and can help us. And in particular, we devised a prediction model in the past based again on a temporal convolutional network, such as the one I've discussed in the case of the remaining useful life estimation for the ball bearing I described in a previous presentation. So I will skip this part. But just to give you an idea, also in the high performance computing center case, having this kind of remaining useful life estimation is a very, very important task. So these are some slides that gives even too many details, but I can share them with you. With this, I conclude. I thank you again for your attention and your interest. And I leave the stage to my colleague now. So thank you again.
Okay, thank you, Andrea. And now we have an intervention from CETIM. Unfortunately, nobody from CETIM could be present at this event, so we have a registered video. So I asked to my colleague if he can start the sharing. Okay, thank you, and please.
Hello, everybody. I'm Roger Buzy from CETIM in France. I will explain to you how we have decided to transfer the results of IoTwins project to the industrial company. So, a short summary. The more important to think is, in fact, to understand exactly what involves this kind of project and demonstrator, taking into account the material part and also the software part, and how customers would use it. And then I will finish explaining in more in depth our approach to transfer the results. First of all, a short description about the work package and the testbed 8. As we know, our goal was to design, to build a digital twin of a machine tool, okay? And the objectives, the main goals were to realize and to help the user in the three major steps of the machining. So first of all, process design at the Bureau of Method, where we have to use digital twin in order to do simulation, for example. Second time, we have the setting phase. The setting phase is a phase in which we try to help the user to do the right setting very quickly in front of the machine tool. And then we have the production phases. And this phase, we will use digital twin to monitor the system and also to make a sort of capitalization of the data it collects. Our demonstrator, in fact, is built on a machine tool, first of all. But on this machine tool, you will have sensors mounted inside. But we need to have an acquisition system to do collect of the data. And the second part, we have to use a PC, which is called Bureau of Method, to do preparation of programs and so on of our machine. And all of these systems have to be connected to the web, to the INFN cloud, in order to access to the software we have developed in this project. On the machine tool, depending of the kind of machine tool, the kind of machining operation you will have to do, you have to instrument with the right sensors. Typically, in turning on this machine, for the part we have decided to produce, we need to have accelerometers, instrumented tools, and also a measure of the power of the cylinder. But in addition, you have also to program the machine. For sure, we have to realize to program the NC program of the machine, but also what we call the script of our sequencer, which is a good way to make a link between what the machine has to do and also when we want to start acquisition, when we want to stop acquisition, when we want to do additional treatment. All of this has to be programmed. Well, after we have the software part. Software part is in fact what we call Bureau of Method. It's in fact software used at the Bureau of Method in order to help the user to do preparation using digital twin approach. Example, we have some images of a screenshot of the software we have developed in this project with ESI and NSAM. Typically, definition of experimentation, CAD interface to visualize the operation, the machining operation, and also visualization of the forces typically computed during this virtual machining. Other softwares are also used in this project to give input to the system, like the quality of the part produced. And then also dashboard to see in real time what is made on the machine. The conclusion of this part, of the software part, is also we have some softwares to use, to master, and we will need to explain to the user how to use them. Then the more important, now we have seen the material part of typically an example of use of our digital twin in the shop floor of the industrial power plant, but also we have also the software part. And then now we have to take into account the industrial context of small and medium enterprise. Small and medium enterprise are not big companies. They have not a very good structuration of the production department because there are few people and not a lot of people. Very often people made a lot of parallel tasks like programmation, mounting, setting, controlling the part, and eventually not only on one machine, but from typically 2 to 10 machines in the same time. So they have a lot of work to do. Another point is people doesn't have a lot of time to spend for new things because as you now you understand, we have they have a lot of things to do. Learning new techniques, for example, digital twin, And also using IA techniques, we will have a small problem because they have no pre-existent knowledge on these topics. Another point, the data that we will record using our digital system shows us that today, a lot of companies have no time to do an in-depth analysis of that data they record. And very often they use only Excel typically to examine, to analyze the result. Last point, and very important, they don't like, SMEs don't like to store their data outside their company. So putting their data, sending their data to the web seems to be a very big problem for this company. Second point, more for technical point, concerning the new techniques like IA, they have no pre-existent knowledge. And they have no possibilities to pay data scientists working and analyzing all the day data. Also, concerning the instrumentation of such machine, as we have made, they have no previous knowledge on how to install, to use, to parameterize the sensors. So it's not very obvious that it will be easy from people to, in fact, to implement a digital twin in their company. So our approach is, in fact, taking into account these small problems. Is two ways, two ideas. First of all, is to make workshop event, like we have made at the beginning of this month of May, with typically 2 conferences in the morning explaining, for example, IoTwins of other projects, and then the afternoon, a presentation in our shop floor on various demonstrators like IoTwin machine. I will show you a short video. I am not the video. Okay, no problem. I will show you after. So we will continue. Sorry. We have also another way, except the event, that is to try and transfer approach. This approach is to go in the industrial shop floor on their machine, taking into account a production type, like a part to produce, installing the material, installing the software, accessing to the web, because we need to have web access, making some production during 2 or 3 weeks, and then at the end, debriefing of the experimentation and estimating the payback. We think that this approach is a pragmatical approach that suits very to the mental point of view of our industry. Typically, we are making today installation in a customer, local customer, local manufacturer, a Go company. We will finish the experiment for the end of July, and we will duplicate what we have made in our shop floor. With machine, definition of a part, installing sensors, using all the software suite that has been developed in this project, and accessing also to the cloud and everything. Okay, in conclusion, digital twin approach is very interesting, but today it's not a do-it-yourself solution. We can say that we need to help the customer because they have not a lot of time to pass on this kind of new systems. So they need accompaniment from us. And then finishing by estimating the payback, because it's also important for these companies to have an idea of what digital twin will help us to obtain. That's the approach we want. We suppose that it's the best for our industrial, and I hope you have understood what we want to explain. Thank you for your attention. Bye.
Okay. So thank you very much. It seems we don't have any question in chat. I leave just some seconds more if someone want to ask something. Otherwise, we think we can close our meeting. Okay. It seems no, and so thank you everybody, and I don't know, Giuseppe, if you want to add something.
No, I was just opening my mic to say bye to everyone.
Yes, okay.
Okay.
So thank you very much, everybody, then, and have a nice day and a nice continuation with this event. Goodbye, everybody.
Goodbye. Have a nice day.
Bye.
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 Bye-bye.